NBPhO computers now have primary control of critical vehicle functions.
Hello. Is the music is the volume of the music good, or should it be quieter or louder? It's good, the music? Hello. Is the music volume good compared to like my voice volume? Okay, cool. Great. Also, is there lag in writing? How is that? Okay, awesome. Okay, I'll just wait for a couple minutes because I said 4:15, and then I'm gonna start. Yo. Okay, I think I'm gonna start. So yeah, I have the problem in the top left corner. That's just problem 1. Yeah, let's try that first. Okay. So solar powered satellite starting velocity V0 is launched from Earth onto an elliptical. Okay. So we're launching a VM with respect to the Earth. And I think the main point is here you have to leave the gravitational well of the Earth. So I think it's just that the minimum velocity is just the escape velocity from Earth. So it's just going to be like just square root 2gm Earth over r Earth. I guess they want us to give it in terms of the little acceleration like g. So we know that little g is like gm Earth over r Earth squared. So this implies that at the minimum velocity is just square root of 2g r Earth. It's kind of interesting. Just escape. I don't know when I'm going to check my answers, because should I do this right now, part A itself? I don't know, we'll see. Maybe somebody in the chat can just tell me if I did it correctly. This is 1A correct? I think I'm just going to wait for that and I'll try part B. So like, what is the speed of the satellite just after exiting Earth's gravitational field? Well, okay, doesn't seem too bad. This is just like, what? This is energy. So this is the M Earth. So this is just the energy originally, and then this is the let's just say V1 is the final speed. I think we just get that V1, and then we can write this as this is just V0 squared minus 2g r Earth. So it's just I guess that would be it for part B. Pretty easy so far. Yeah. Okay, it looks like part C is significantly harder. Okay. Let's check it out. Express the long time average solar irradiance of the satellite in terms of time-meter axis A, angular momentum J, orbital period T, and mass M. Okay. So, okay, first of all, I'm just confused about how they're phrasing it because it looks like capital T is just a function of A. So it's just weird phrasing. Isn't T just like T is just a function of A by Kepler's third? So it's not really like T is any extra information. Okay, fine. And then I guess if you specify I'm trying to just think like I might be really stupid here, but if you specify A and you specify J, that's not enough information to determine the trajectory, right? I mean, you might not need it anymore, but like isn't there like for an elliptical trajectory? Or maybe it is. Okay, cool. Anyways, whatever. So let's figure out. I think they don't want in terms of mass the sun. That's why there's both T and A probably. Oh, okay. I mean, they gave us the sun's mass at the bottom as a variable, so shrug. I mean, yeah, okay, whatever. It doesn't. That's yourself the problem, I guess. Long time average. Okay, so solar irradiance. What is irradiance? Is this like, yeah, I mean, it's fine. So what is solar irradiance? It's like, is this just like the power per unit area on the satellite? So they haven't really given us any information about the geometry of the satellite. So I'm just assuming that the satellite always has a constant area facing the sun, so that's not really a factor. Like, they don't really care about like if the satellite is its orbit, there's different areas angled toward the sun, so assume like the solar panel is always facing the sun. Then I think we're just gonna be I forgot exactly how luminosity works, but isn't it just like we're just trying to find the average of luminosity over 4 pi r squared over the orbit? Is this how luminosity works? L over 4 pi r squared is the irradiance or something? Can somebody tell me? That's right. Yeah, okay, power per unit area, that makes sense. But is it just L over 4 pi r squared? Is that how luminosity works? Like, what are the units of luminosity? I think luminosity is like watts, right? So I think L over 4 pi r squared would make sense. Okay, so you just want the average of L over 4 pi r squared. So let's think about that, I guess. Oof. So what is average of L over 4 pi r squared over the orbit? L is a constant, so it's just L over 4 pi average of 1 over r squared over the orbit or something. Okay. Now some elliptical orbit. I want to find the average of 1 over r squared. I mean, I don't think we want to like write out a whole explicit trajectory. Like I don't think we want to write out like r vector of t as a function of time and literally integrate this. That would be too messy. This is probably a slick way to do this. Okay, so let's use the standard polar coordinate setup. So let's let theta be our parameter. So we have that this is, so let's just say average of 1 over r squared is just integral from 0 to 2 pi of 1 over r squared. It's like, well, it's okay. Let's do this. It's like 1 over the period times integral of r squared dt. But I want to relate dt and d theta, right? And I can do this because of Kepler's second law. So how does this work again? Okay, so something with j here is going to be this. So how did dt and d theta relate? I guess we just have that like how does this work? So like you have d theta. This is r. So Kepler's law will just say that r squared d theta over dt is equal to a constant, right? Because r squared d theta is proportional to the area, dt is the amount of time. So what is the value of this constant? It should be related to the angular momentum. Let's figure that out. So oh, right. So isn't this just straight up equal to the angular momentum over m? This is how it works, I think. Yeah, so this is Kepler's second law. So essentially what's going on here is that r squared, this is equal to essentially r times r d theta dt. And r d theta dt is essentially equal to the tangential velocity. It's just the velocity. Well, okay, so I guess this is not correct. Hold on. Wait. Look. You're barely, when you're talking, it looks like you're barely here. It's so bad. This is okay. Can you hold it up for me?
Is the mic better now, potentially? Because I was told the mic sucks right before. Is the mic better now? Much better? Okay, excellent. That's good. Good. Awesome. Okay, so somehow I'm like right now I'm tilting because I'm forgetting how Kepler's second law works, but that's okay. I'm just trying to interpret this as angular momentum. Why is this so difficult? Right. Yeah, okay, no, this is fine. So basically the point here is that r d theta dt is the component of the velocity that's perpendicular to the radial element. And then dr dt is the velocity that's parallel to the radial direction. So r d theta dt is the thing we want to multiply r by. So this is essentially r, this is proportional to r cross v. So it is j over m. Which means that dt is equal to dt is equal to r squared d theta over j over m. Bro, now I'm more confused because this now is telling us that this is m over jt times integral of r to the fourth d theta. How are you supposed to evaluate that? I was hoping the r squared would cancel out and then this would become really simple. I think I'm making some really stupid mistakes here. But I'm just not sure what I'm doing wrong right now. Oh yeah. Of course. Yeah. You're right. It's complete. I just miscopied here. Yeah. So that fixes everything, right? And this becomes shit. Oh, sorry. This just becomes d theta. So this becomes 2 pi m over jt. Likable outlier. Yeah, probably should. I'll change that for next stream. I'm not sure how to change it right now, but yeah. Okay, wait. So this is spilling over. It's not good. So then the answer supposedly is like, if we consolidate this, it's like L over 2 times M over JT. But I guess somehow they wanted it. They don't. Okay, they want MJT. Okay, I think this is the answer. Yeah, I think this is just straight up the answer. Am I going to do math next stream or later? I'm most likely going to do. Yeah, I'm most likely going to do some sort of math problem solving in a later stream, probably next stream. Yeah, I just wanted to do this physics Olympiad today. I was going to might as well stream it. But yeah, I'll probably do some sort of Olympiad math next stream, for sure. Can somebody like pull up the solution and check this, because this is like, this part was non-trivial, so I'm not really sure if I did it right. Can somebody check this answer? Then I'll do part D. It's right. Cool. Good stuff. All right. Nice that was a nice part. I think the problem writer just realized that they can, that 1 over r, the average of 1 over r squared is solvable nicely, and then they invented this solar irradiance thing as a way to get people to test to do average of 1 over r squared, because it's kind of unnatural, I feel like, the setup. But obviously average of 1 over r squared is nice, so it's fine then. Okay. I guess we can try part D now or something. What is the maximal average solar irradiance needed? Ooh. Launch angle with respect to Earth. Oof. I don't like this at all. Because you know, I have to deal with the Earth motion and stuff like that. Oh man. Wait, I'm a little confused right now, actually. Relative velocities in space is really confusing to me. Wait, so actually I'm gonna try something. I'm not really sure if this makes sense, but let's go back to like part A. This is like the escape velocity part, just very simple, right? Very obvious. Minimal velocity speed required to reach any heliocentric orbit. But here v0 is assumed to be with respect to the Earth. You launch with speed v0 with respect to the Earth. But what if the Earth... So let's just like, can we just think about part A again in the following way? This is the Earth. But say the Earth already has some velocity like v2 going this way. And then I launch with v0 with respect to the Earth, so I'm actually launching sort of with the speed v2 plus v0. That's sort of my launch speed instantaneously. Yeah, I think the issue is that like you can't really do energy conservation when the gravitational source field is moving or something. Because if I try to do energy conservation here to find the escape velocity, you don't get the same answer because like the energy equation does not shift linearly if you make all the speeds go up by a constant amount, right? Like if you look at this equation in part B, 1/2 mv0 squared minus gm, if I like increase v0 by v2 and I increase v1 by v2, this equation is no longer satisfied. And this equation no longer works if I replace v0 with v0 plus 10 meters per second and v1 with v1 plus 10 meters per second. Which means that it's important that you do this calculation in the frame of the Earth. So somehow like a moving gravitational well will create weird stuff. Is that a correct thing? You have to do in the frame of the Earth, right? I mean, yeah, I'm pretty sure, because otherwise there's no way for this to make sense. Okay, this is just sort of intuition for how you'd solve part D. Anyways, so part D, what we're saying is, okay, so by the way, for part D, it looks like I think we just want to minimize JT, because L, M are obviously constant. So, let's say this is the sun. This is the Earth. The Earth is already moving with some velocity, I'll call it v2. But then with respect to the Earth, you launch it with v0 at an angle something, something, something. So I think what you get, this is North Balkan Physics Olympiad 2019, problem 1. Or not Nordic Baltic Physics Olympiad. You can find it on Jan Kalda's website. Yeah. The problem statement is in the upper left corner, but yeah. Okay, so if you launch with speed v0 relative to the Earth's motion. So let's say you launch with speed or a velocity v0 like this, angle theta. Then in the reference frame of the Earth, what's going to happen is you actually are going to have like you're actually going to have like, so let's just let this unit vector in parallel to this guy. What the hell? Just like v0 hat, I'll call it v0 hat. Then my actual final velocity v1 once I leave the well of the Earth. This is actually v0 with respect to Earth, so this is kind of a bad picture. Will be square root v0 squared minus 2g r Earth. Is that what we got in part B? Yeah. Times v0 hat. Because that's when you leave the gravitational field of the Earth. But then you have to add on plus v2. So the actual velocity, if I call this v3, this is the actual velocity of my object. Where this is, again, the velocity of the Earth. Okay. And square root v0 squared minus 2rg Earth is constant because v0 is constant. So essentially you just have like a v2 and you can add some vector of constant length to it in any direction. So you want to minimize j times t. So I think j is minimized, like, for example, j will be minimized if you take the angle theta to be pi. Exactly opposite, because, no, is that true? Okay, that actually might be false. Hold on. Yeah, that's not true. Never mind. Oh, no. It is true because this picture is misleading because I need V2 to be perpendicular to the line joining the sun and the earth, because we can assume that the earth is in a circular orbit. I hope. Yeah, earth is a circular orbit. I think that's implicitly assumed. So I guess this picture is kind of misleading. The sun is actually somewhere down here, and this is a right angle with V2. Okay, JT. Okay. So I'm gonna let this guy be this quantity just be U. It's some fixed quantity, because that's just some quantity that like is in terms of stuff that we know. So I think what the problem is really saying now is that you have the sun, you have the earth, and the earth has some natural velocity v2. But now you have this extra velocity u, which you can add on in any direction. So you have sort of this free angle, and then your velocity is actually going to be v2 plus u. And you can launch it like this at a radius earth, and I think that we'll just call this capital R. And you want the j times t to be minimized. So j times t to be minimized. And here j is the angular momentum, t is the period. Okay, how do you do this? So j isn't j, I'll just work with j over m. I'll just say j over m times t. Isn't j over m just equal to rv2 plus ru cosine theta? So that's j. Now I just need to solve for t in terms of theta. So how do I solve for t? Well, t is obviously proportional to a to the 3 halves. Okay. I forgot the exact form of Kepler's third law, so let me try to figure it out. It's like, oh crap, what the hell was that? Oof, what is the Kepler's third law? It's like 4 pi squared g m sun over a cubed, maybe? No, the a cubed has to be in the... how does this work? Well, okay, let's just... The hell? Oh my god. Wow. My screen sharing stopped working. Okay. That was unfortunate. Okay, I think I'm actually gonna probably like turn off notifications. That's probably a good idea. Give me a sec. I thought I already had notifications turned off, but I guess calls still come. But yes. Okay. So let's okay, yeah. So somebody gave me the formula because I was just not remembering how this works. A cubed over GM. Okay, yeah, this makes more sense. So I guess we want to like figure out what is A. And the way you figure out what is A is you go like the total energy of the orbit is negative GMM over 2A. And then this is equal to negative GMM over R. And again, if I let this be V3, then this is plus 1/2 mv3 squared. So A you can solve for like this. Now this is pretty bad. But like, I think the key here is to notice that this left-hand side is an increasing function of A, for example. And this right-hand side function, therefore, this right-hand side function is minimized when V3 is as small as possible. So in fact, I think I noticed before that J is minimized when theta is equal to pi. Because the angular momentum is linear, so it's just sum of the thing from V2 and from U. And V2 we already know what it is. And you just look at this expression, right? So theta equals pi is the minimum. And I think we notice here that theta equals pi is the minimum, again, because you want the V3 absolute value to be as small as possible. I think. I think this is right. Yeah. And this only works because V2 is perpendicular to the sun, the line joining sun and E. Otherwise, the minimums would not be the same place. But this is minimized when V3 is as small as possible. So I think we would just notice that theta equals pi is the minimum. And what is the maximal average? I'm not going to actually calculate it. I've given it all enough information to calculate it. So you just would take, V3 to be, essentially you would just take V3 to be the speed of the Earth in its orbit minus U, which is V0 squared minus 2gr Earth. And then you would calculate, you can calculate A in this way. This is how you get A. This is how you get T. This is how you get J. It's just now RV2 minus RU, and then you just plug it in and you get JT over M. I'm not going to calculate that. I think the key in this problem is to notice that theta equals pi to the minimum. So what this is saying is that it's optimal to launch it exactly opposite to the Earth's velocity. Can somebody check if that's right? To launch this exactly to the Earth, opposite to the Earth. Awesome. Thanks. All right. Awesome. Okay, let's try problem 2 now. So let me edit this. Make this problem 2. So that's changed. Now I have to change the problem, the actual PDF to get to problem 2. Oh man, this is so annoying. Problem 2 is over multiple pages. Oh no. Can you fit this all on the screen? No, this is just impossible. Skip it? I'm not gonna skip it. We gotta go in order. We'll just move around, I guess. Just be stupid and move around like that. So, number 2. Maybe screenshot and put it on Paint. Yeah, that's true. If I was less lazy, I'd probably do that. But I don't think I'm gonna do that. If it gets annoying, then we'll see. Wait, what is Tavid? Dan is asking something. Correlation between being named, called, and being cracked at physics. Okay. Nice. Yeah. Taved is Calda's son. Is he in high school? Does he like do physics contests? Did he do physics contests? Nice. That's cool. I mean, if your dad's Calda, you probably are doing. You have good access to like physics questions and stuff. You have good access for answers and things like that. Nice. Okay, I'm gonna start trying prompt 2. Yeah, I mean, like if Calda's your dad, then you can like ask him questions and stuff. He'll be able to answer. He'll have access to those kinds of questions and answers at a young age, which is pretty helpful to like get good at any sort of thing. If you're able to have that resource at a young age, being able to ask questions to somebody. Anyways, we can try prompt 2 part A. Okay, part A looks trivial. It's just 2 pi root m over k. I'm pretty sure there's just nothing at all special about this. This is just a spring. Okay, so now I'm gonna have to move around. Okay, but the picture is actually not bad. Like, let me just draw it right here. So it's like, you have a cylinder of radius r, homogeneous, so it's in one dimension, it's 1/2 mr squared. Mass m, and it's connected by a spring to the wall with spring constant k, and yeah, that's it. And then there's a coefficient of friction mu. I guess it's not clear. I guess they're assuming static and kinetic are both mu, something like this, I assume. So let's move to the, what does it say? The roller is pushed aside and starts to roll back and forth. For small oscillation amplitudes, there's no slipping between the roll and the surface. Right. Oh, okay, fine. Okay. This should be relatively simple. So, I think the easiest way to do this is suppose you roll an angle theta. Then what you end up getting is that let me think. So you roll an angle theta, then you have some sort of friction force. Okay, so what you end up getting is that like or maybe angle theta is not good. Let's just do x. you go out a distance x like this. So you have that kx minus mg mu, or actually I should be saying like just Newton's second law tells you that mx double dot is equal to, so the thing is trying to roll backwards, so I guess what's going to happen is that you have the spring wants to pull it backwards, so you have friction. You have friction pointing to the. You have friction pointing this pointing. Well, that's not friction pointing to the left, I believe. Well, it's not mg mu. It's just some friction, because it's static friction. Minus kx. So you have some friction pointing this way. And then you have, in rolling without slipping, the angular, so this is the moment of inertia, and the angular acceleration is, x over r is the amount of angle, so it's just x double dot over r, I'm pretty sure, just a over r. That's just how rolling without slipping works. So that will be accelerating this way, and this is just equal to negative FR, I'm pretty sure. So if we eliminate F, also, I don't know why I had R in two different sizes. This thing should just be R. Okay, so F is equal to negative 1/2 mx double dot. So then this implies that 3/2 mx double dot is equal to negative kx, so x double dot. So the period is equal to 2 pi root 3m over 2k. And just as a sanity check, this thing is telling me that the period is larger, which sort of makes sense, because the way I think about it is that like now it has to all sort of account for like rotational energy as well, and sort of it's like lumbering around. You can think of it as effectively lumbering around more mass, so the oscillation will be slower, so the period will be larger. This makes sense. Can somebody check this though, because this is a sort of a calculation. I'm not sure if I did this right. By the way, we got rid of this idea. Yes, can somebody just check if this is correct? Oh, yeah. Yeah, okay, Dan points out a faster way to do this. Yeah, the effective kinetic energy is just essentially just 3/4 mv squared now instead of 1/2 mv squared. So yeah, that works. Okay. Part 3. If the initial oscillation amplitude is larger than a critical value A star, the amplitude of oscillation starts decreasing in time. So actually doing part B using forces was actually helpful for part C. Basically, part C is asking us when is kinetic friction going to become a big deal. This is actually now, given what we've done, very easy. So we just solve for friction, right? Friction is negative 1/2 mx double dot. So we essentially just need 1/2 mx double dot. So this is, I'm trying to solve for the static regime. Is always has to be less than or equal to mg mu. If this is ever violated, you're done. You're screwed. But x double dot in terms of the amplitude, the maximum acceleration, in terms of amplitude, is just a omega squared. Yeah, a omega squared. And omega here is the sort of omega r is root 3, or is root 2k over 3m. it's just omega squared a, so it's just going to be 2k over 3m times the amplitude. And we need this to always be less than or equal to 2g mu. So this implies that this sort of a star value that I care about is equal to 3mg mu over k. Can somebody check this? Part 3. Okay, awesome. Awesome. Okay, let's just do part D, and then part E looks really annoying because it's like qualitative graph, but I guess we can try our best. Okay, part D, assuming the initial amplitude, what is the maximum angular speed of the cylinder during... Okay. So we can assume that we very quickly get into steady state of constant friction, I assume. And they said 0 between... they said t less than or equal to capital T over 2. So you're always going in one direction. You start all the way out and you keep going until you stop. Okay. Cool. Let's try part D. So now my equation looks like mx double dot is now equal to is the friction always going to be pointing to the left? Yeah, it always is. It's pretty clear. So we have this now. And x of 0 is equal to a star. X, the initial velocity, is equal to 0. So this is just a shifted simple. This is just a shifted simple harmonic motion. Yeah. So I guess the maximum speed would be when you pass through the equilibrium point. So sort of the equilibrium point now is some sort of x0 equals mg mu over k. Wait, am I trolling here? Am I like completely missing like rotational stuff? I feel like I'm completely missing rotational stuff, but somehow that doesn't matter. Buy followers and viewers. What the hell? Wait, guys, am I like missing something? Because I'm not. This is not going to involve the rotational aspect at all. Yeah, this looks like a scam for sure. Let me like delete the message, I guess. Okay, great. Isn't it easier to use energy here? Maybe, but I don't see what's wrong with my approach. But I'm confused just because I'm not using rotational anywhere, but I think it's fine. So maximum speed x0 is when you pass through the equilibrium point, I guess. What is MMP? Oh, method of moving points? Oh. Maybe. Possibly. Yeah, maybe I can do that at some point. But, yeah. That's a good idea. Yeah, maybe. Yeah. Okay. So, it's when you pass through mg mu over k. But yes, now I'm Dodgers 66. You're right. Like, the way to get the speed now is using energy, I think. Yeah, exactly. Rotational wants to get alpha I. But yeah, but no. Now to find the actual velocity, I think. Well, no. I still don't see it. Isn't it just like now? Isn't the answer just But they told us A0 is much larger than A star, which is. What? Okay, I claim the answer is just A0 root K over M. Because all the effects, all other effects are it's this plus O of A0 over A star, which we're ignoring. Is this correct? Is this what the solution says? Because seems a little suspicious to me. Is this the answer? Is this the right answer? Can somebody check? No, the answer has mu. Okay. So now I'm officially confused about this part. I don't really understand what's going on. Maybe like... Oh, I don't see how that's relevant. Wait, can you tell me what's wrong with my approach? I want to know what's wrong with my approach, like the way it's set up right now. Like, do you agree that this is the equation of motion after it goes into the sliding regime? Is this the correct equation of motion once it goes into the sliding regime? Or is this wrong? Because if this is right, I don't see why the answer I wrote down is wrong. But we don't care about the angular velocity, right? Oh, maximum angular speed. Oh my goodness. Oh, okay. They're asking for angular speed. Oof. Oh, I somehow read this as maximum linear speed. Okay, you're absolutely, yeah, okay, yeah, you're right. Oh, we need the maximum angular speed. Okay, I just misread the question then. Oh, crap. Okay. Yeah, okay, so now we have to get the angular velocity. Yeah, so torque is the right way to do this. The torque, and we take angular velocity to be positive clockwise. So friction is helping. Right, friction is increasing the angular velocity. The torque is just the friction times R. But very quickly, static friction, it becomes kinetic friction very quickly. So it's just mg mu R. And we have this for basically like all the way till you reach the equilibrium point. So pretty much this is constant. So we're pretty much saying that this thing will constantly speed up. A constant rate. That's kind of interesting. So the omega final is just 2g mu over r times the amount of time it takes to reach the equilibrium point. So it's just 1/4 of a period. And here the period is just k over m. So it's just 1/4 times 2 pi root m over k. Okay, is this answer correct? Does this even have the right units? Meters per second over second. Yeah, this is correct. Is this the final? Is this the right answer? I think Dodger's message saying yeah was for something previously, so I don't think it's been answered yet. There's no pi. Wait, but Turtle said there's no pi at. Where's that? How is that getting resolved? Because there should be a pi. How is there no pi? That doesn't make any sense. Oh, the answer is in terms of capital T. So you're saying the answer is g mu over r times t? That's what they're saying it is? It should be 1/4 of the period, right? Because that's when your maximum, the speed is. Oh, I'm just being stupid. No. Half the period is right because the angular speed is always increasing till half the period, until the friction direction reverses. So no, you're absolutely, the half is that. This is just a silly mistake. No, half is right. Half is right. In fact, let's just write this in terms of t. Omega f is just it's just this. Wait, Dodgers, do you understand why it should be 1/2 instead of 1/4? Because like what happens is that as long as the cylinder is moving to the right, it's always going to keep increasing. Yeah, no, I made the same mistake because it's only 1/4 if it's the velocity, if you're doing linear velocity, but angular velocity will keep increasing no matter what until the frictional direction changes, and the friction direction changes at t/2 because that's when the cylinder starts moving the other way, due to the linear. So you keep going till half the period. Okay, that's actually kind of tricky, like because we thought linear velocity and then we forgot to do it for this. Okay, but yeah, I think this is part D. It's just the answer is correct, right? G mu T over R. I assume. Qualitative graph. I do not want to sketch a graph. I really don't. Maybe let's think about it to see if there's anything interesting, but if it's kind of dumb, then maybe we'll just skip it. So same setup, sketch a qualitative graph showing the dependence of alpha and A as functions of time. Okay. I mean, okay, I guess we can try this. No, we don't want the text thing. Okay, so E. So here's time. Here's like T over 4. Here's T over 2. So alpha R is constant at 2g mu. Well, okay. Okay. So let's be careful. Let me actually just do this again. I'm using just notes in. I'm just using notes in iOS. That's just my iPad. Yeah. Okay, so I think we want to sort of have positive and negative. Okay, so the angular acceleration is first constant at 2g mu. This is 2g mu. I guess it's, to the left. But once the thing starts going the other way, it would just be the other way, I think. So then it just sort of then goes like this. This minus 2g mu. And then for A, for the linear one, it pretty much just has a harmonic motion. So A is proportional to x in harmonic motion. So it's just pretty much like a cosine curve, I'm pretty sure. So like, but it starts off at kx. No, but it's just cosine, but I think what does it start off at? That's the question. Compared to all this, it starts off at just like it starts off at kx. So it's just ka star. So let's just say it's like, let's say this is just ka star over and note that this is completely way off the scale because not a star. It's not even a star. It's just ka 0. But note that ka0 over m is much larger than g mu because we said a0 is much bigger than a star. So this graph is misleading in that sense, but that's fine, I think. Oh crap! It has to go down to like negative ka0. Drawing is hard. Okay, is this correct? I think this is correct. Is the graph for A, the angular acceleration, correct? But in reality, this is much smaller, so like in reality it would look something more like, and then like a huge cosine curve. In reality it would look like much more disparate like this. This might be a better picture. So I'm actually gonna pull up the solution just to see if it looks okay to me. Called let me just check the solution. Yeah, this is correct. Awesome. Yeah, this is exactly correct. I'm a senior. Didn't somebody come in with Wiwa? And now it's William? I'm confused. Oh, William. Okay, this is somebody else. Oh, okay. Makes sense. I get it now. Hi, William 65538. Also, I'm gonna be back in just a sec. Hi. At Bobby Bob 356. Yeah, hopefully. The hope is to stream regularly. I mean, I don't know if I actually will, but if enough people keep coming and if enough people are interested in what I have to say, then I probably will. Yeah. It's gonna be a lot of math as well. Maybe math contest problems as well as other kind of math. Probably mostly math contest problems. And physics stuff as well. Because that's what I do. I do math and physics, so that's what this stream will be. This problem 2 was pretty... I didn't like it. I like problem 1 a lot better. The orbital mechanics problem. Yeah. Maybe I'll do one more. I was planning to go till for another hour, another 30 minutes maybe. And then stop around 6 p.m. But yeah, we'll see. Do I play games? I will probably... I might like try to play chess. I'm really, 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 really bad at chess. Like I'm like 1000 rated or something, like 1050 or something. Want to play Minecraft? No. Which ones? Okay, no Minecraft. I only game I play on the computer is chess.com. I just play on chess.com. But yeah, like I said, I'm pretty bad. I like blunder a lot and stuff like that. It's kind of sad. Yeah, maybe I'll like stream myself playing chess sometimes as well if I'm tired of math or physics or whatever. Yeah, but I don't play any like traditional computer games really. Do you like games like CS:GO? Is this like Counter-Strike? I mean, no, I have like I've never played I've never like played any sort of like real video games like PC games or like console games. So yeah, I mean I don't know if I like them or not. I never tried. Yeah. So I don't know. So how's the music? I've turned off the music for myself, but everybody can hear it, right? That's how it's supposed to work. This is my first Twitch stream ever. Well, technically I did a stream yesterday with just like 2 viewers. That was just a practice stream. Not practice, but just like to see if I understand how Twitch stuff works. But I didn't have any music then, and it was much more basic than this. Yeah, this is my first stream. This is pretty fun. I feel like I enjoy this. Yeah, I'm enjoying this quite a bit. This is pretty good. Do I play Surviv? I played Surviv like 2 years ago. By the way, why is there such a lag between the chat and the video? I think this is just a standard Twitch phenomenon. No, I don't really know. Do I play Agar.io? Wait, Agar.io is like the Agar.io is like the cell game, right? Where like the cells merge and stuff like that or something, right? So, I think I played that like maybe like 5 years ago. Baba Is You. No, I don't play Baba Is You. I've kind of wanted to play Baba Is You at some point, but like it's like I think it's probably too big brain for me. Like I'm just not good at like puzzles or just like thinking problems. Yeah. Maybe I'll try Baba Is You at some point. Okay, this is a bot, so I assume should be deleted, I guess. This is not a bot. I deleted it. It's real. This looks like a bot message, bro. I'm not convinced that this is real. At what age have I started doing Olympiad math? I was doing contest math till like I like I started contest math, but I started contest math. Wait, what am I trying to say? I've been taking AMCs and stuff since like 4th or 5th grade maybe, and I did math counts in middle school. But I started preparing for Olympiads sort of like in 8th grade. I did Woot in 8th grade maybe. Yeah, Ops Woot. But I didn't do it very seriously in 8th grade. And then I did well on the JMO in 8th grade. So then starting 9th grade, I had started doing Olympiad math pretty seriously. And then I've been doing it seriously till now. But yeah, I've pretty much stopped doing Olympiad math now because I'm a senior and I'm done. So I'm still gonna do some on stream. I'm still gonna do some on stream, but not for my practice anymore. To get so I think in 9th grade I prepared enough to get to like MOP level where I could sort of have a good chance at making MOP. And then in 10th grade I sort of stayed at the same level. And I went to MOP in 10th grade, and then after 10th grade the year between 10th, like the sort of the year right after MOP 10th MOP 2019, I prepared a lot. And then I don't know, like just I sort of went from MOP level to sort of close to IMO level in basically like a few months after MOP 2019 because I did a lot of practice then. IMO level depends too much on the year. Wait, really? Wait, IMO level is just like... Isn't IMO level like, I would just say IMO level is somebody who can say that they will be able to consistently win USMO or something. I don't know. Something like that. I think most people who make IMO or are close can probably consistently make top 12 on USMO, no matter what test it is. Or like pretty close to that. Is getting to MOP in 10th like a bronze IMO medal? I think so. I think getting to MOP in 10th is probably the same difficulty as getting an IMO bronze. That sounds right. Yeah, I agree with that. Maybe IMO bronze is slightly easier. I think it's pretty comparable. You have to solve like 3 problems. You have to solve 3 problems on a medium difficulty. Wait, okay, no. I guess maybe like getting MOP in 10th is like getting a low silver or something. Yeah, green used to be 2 problems. Well, now it's always at least 3 problems, unfortunately. It seems so. But to be fair, the tests are a lot easier nowadays compared to before. Like, it seems these days 1 of 2 and 5 is always at like a USMA 1-4 level. Feels like that. Whereas if you go back to like 2018, both 2 and 5 are pretty hard. 2017, both 2 and 5 are pretty hard. 2016, both 2 and 5 are pretty hard. Whereas nowadays, 2019, you can see 2019 5 maybe it's not that hard. 2020 number 2 is maybe not that hard as those other problems. 2016 USMO 2 is hard, yes, objectively. 2016 USMO 1 is also hard. Or not 1. Actually, yeah, 1 is also kind of tricky, right? And 2016 USMO 4 is also hard. 2016 is really weird, where it's just like... USMO is just weird a year, I think. Who enters moving points? I think Anant. Ananth was the first person I saw in AOPS to consistently use moving points on solutions. Yeah, but then like I think me and Zach then started like figuring out how to do moving points for more than just projective case. So yeah, I'd say like Ananth, me, and Zach Roman, Ananth Mythical. Animation sounds a lot cooler. Yeah, but I think moving points is stuck. Whether you like it or not. At which college are you? I'm currently at home. Not at college. But I'm probably gonna go to MIT. Actually, I'm definitely gonna go to MIT. So, yeah. I'm gonna go to MIT this fall. MIT is a smart people school. Questionable. Gap year? No gap year. Did I commit already? No. I'm not committed yet. But I will with like a 99% chance. Actually, like the reason I haven't committed yet is because I haven't like... Because committing requires a lot of effort. You have to fill out a bunch of stuff. So that's why I haven't committed yet. But yeah, I'm planning to. No, I've decided. I've definitely decided. I just haven't filled it out yet. I don't really want to do linear physics problem. This is kind of done. Let me just see if the third problem looks fun. Particles with mass, I'm okay. Oh no. These problems are so standard but so annoying. Yeah, I'm definitely not doing this problem right now. There's no way I'm doing this. Yeah. Maybe I can do a math problem right now. Kind of done with physics for right now. Yeah. After MOP 2019. I think I got a lot better after MOP 2019. From like July to like December. And then I've never gotten better since, pretty much. Gotten a little bit better since December of 2019 till now. The progress has been very, very slow. And arguably I've like regressed in some areas as well since then. Like geometry, for example. What do you mean how much? Why I regressed in geometry? I regressed in geometry because I stopped caring about doing geometry problems. It's kind of sad. Maybe I should have maybe grinded geometry more. Maybe. I don't know. Geometry gets so dull after a while. Like, there's no more magic to it anymore. It's just mechanical. Yeah. Yeah, geo sucks. Yeah. Occasionally geo can be nice. But I only like when geo is nice when you can solve it in some very unconventional way. Like if it's just a bunch of like, well, see, the thing with TELV is TELV-COL is on a complete other level in terms of geometry. Like some of the stuff that TELV-COL does, like I don't even like. Well, not some. Most of the stuff TELV-COL does, I have no idea what's going on. So TELV-COL is like doing geometry on like just another level compared to Olympiad, I think. Combo or NT. I like all of ACN equally. They all feel like the same subject. They all feel like real math, whereas geometry just feels like a sore thorn. It feels like unnatural and out of place. But everything else just feels like math. Everything else is just like math. Geometry is just like something else. Yeah, I agree with Wiwa. A equals C equals N. Much better than G. Yeah. But also I feel like geometry nowadays has become harder. I feel like every single geo problem now, there's no longer none of that easy, like nice geo, like you just like draw some stuff, you just figure out like, oh, this point's on this circle, blah 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 blah, and you're done, right? Now all geometry has to be like weird. It's like let's look at like the USMO number 6. It's like, why is this like a problem? Like a hexagon, like is just unnatural. And every single geo problem now, basically, if you have any sort of like a regular geo problem, then people are so well trained now that it's just easy. So not only like USMO 1, I mean, I think USMO 1 is probably like, I'm not saying I like geometry, which is just like point, like just circle, point, figure out some stuff. I'm not saying I like that, but at least I feel like I'm good at that because I've practiced it a lot. I don't like necessarily like it still, but like geo where like it's like a weird setup, but like I'm okay with a weird setup if you can come up with like a nice sort of like algebraic solution or something. But like if the solution is then just some random synthetic thing, then it's just feels very unsatisfying. But this is the trend because it's not hybrid geo. Hybrid geo is where I like hybrid geo. I like hybrid geo. I'm talking about purely classical geometry problems with weird setups. I mean, I don't like them because they're hard and I don't know how to do them, but I also don't like them. I mean, the thing with weird geo is you can do weird geo in like cool ways, like cool applications of complex numbers or something. But like USMO 6, for example, it's just some random synthetic idea. And if you don't come up with this random synthetic idea, then the problem is completely intractable. So you're not solving the problem by understanding what's going on. You're solving the problem by coming up with a random synthetic idea. And it works. Berry bash? Well, you can't berry bash that problem. But it's a pure berry solution, if I recall correctly. I mean, I can almost guarantee you either that solution requires like an infeasible amount of computation, or it involves a clever synthetic setup observations, which render the berry part useless. Like, if that solution involves enough synthetic ideas that you can just solve it synthetically from there, like it becomes easy synthetically, then it's not really counting as a berry solution. Like, an example of a geometry problem which I like, and I'm just biased because I also solved it. It's like the February TST. This year's February TST problem 2. Because I had a solution which did just involved understanding like how the points moved or something. So like if you if you figure out like sort of like what's going on in the problem, and then it sort of was true for an algebraic reason, and that was very nice. But USMO 6 is just true for like a very, very like not contrived, but just very like random synthetic reason, and like if you don't see that synthetic reason, then you just don't know what's going on. And yeah, it was by Colin Tong, so like obviously nobody's gonna be able to do it. Wait, can somebody send a link actually? I want to see, because I don't see how you can berry bash this problem without coming up with a significant synthetic observation, which would already make the problem easy enough to do without barycentric. Yeah, okay, so great. Like, let's look at Colin Tong's solution. Yes, obviously it's possible, because they're both polynomial relations, right? So they have to be the same polynomial, so you know it has to work. But it's completely infeasible. Completely infeasible to do. Is TST 2021 much harder than other years? Which one? What do you mean? Like, there's 4 TSTs. Was the TST cycle much harder than other years? I don't know. Was a specific one harder? I don't know. Yeah, I'm not sure what you mean. Also, somebody asks, berry bash or moving points, which do you recommend? I mean, it depends on the problem. And you can't really understand moving points well unless you're good at berry, in my opinion. Like, if you're not good at berry, in my opinion, I think you better get good at berry first before trying to learn moving points. Oh, 2021, that TST? That TST is weird because problem 1 is easy, problem 2 is this sort of very hard geometry problem, and then problem 3 is straight up a homework problem. Like, number 3 is a difficult math homework problem. It's completely unsuitable for an Olympiad. So, like, number 3 would not be out of place on a real analysis problem set at a college. But somehow it's an Olympiad. Yeah, exactly. I agree with William. Like, you technically can learn, like, the mechanical method of moving points. And you probably would be able to, execute it well enough to do easy moving points problems, but you won't be able to do it in any, like, sort of non-trivial way. How many points did it have on that day? I'm not sure if I want to say on public stream. DDIT may be good to know before also. Yes, I agree. Actually, like, I made a projective geometry lecture series. Not a lecture, yeah, basically a lecture series. At Math Camp 2019. So I have like I have like 20 pages of handwritten notes about just doing projective geometry from scratch. and it includes DIT, and it includes moving points and stuff. And I gave that lecture at math camp, for a math camp event, but maybe I can give that lecture again on Twitch. I don't know. We can see. They're handwritten, so it's hard to oh, low battery. They're handwritten, so I'd have to type them up. But yeah, I might adapt them into a Twitch stream or something. Publicize a lecture or something like on projective geometry techniques, including moving points and stuff. Yeah, I might do that later on. Yeah, for sure. Yeah, I'm gonna think about doing that later on. Mm-hmm. 18 viewers in here. That's a high. Anything people want to talk about for like the next 10 minutes? I'm probably going to leave in 15 minutes exactly from now. So I'm up to do anything that people want right now. Math, physics, talking about anything. So I'm just doing nothing for 15 minutes, pretty much. Any suggestions for what to do? No suggestions for what to do. That's really sad. People don't want to do anything. Let me try something. Let's go to this other scene. Okay, I don't think I want this. Let me... This. Okay. This is this. Let's just try chess. Even though I'm really bad, let's just give it a try. Or maybe, yeah, let me actually not do this. Let me go back to the go here. And try chess puzzles. I don't know. Nobody's trying. Nobody wants to say anything. So let me try this. Even though I'm like ridiculously bad at this. So I think we want to checkmate the king here. Queen to h3 looks not bad here, but I don't know if that's the correct move. I feel like the king can then move down. Queen to h3 looks like the right move here. But then the king can move to f4, and then I'm not sure what happens. Let's just try it. Crap, it's wrong. Oh, no. Oh, is rook to h3 the checkmate? That's checkmate, right? Wow, that's kind of insane. Okay, oops. Stream is not loading. You serious? I don't know. I think queen to g3 looks good. Queen to g3 forces the king to move to f1. So if the king moves to h1, then it gets mated by if I move the queen up 1. So queen to g3, king to f1. But then there's no checkmate. I don't see the checkmate then. I don't know. I'm just gonna try it. Okay, it's right. That's what I thought. But now there's no mate. Oh, there is. There is mate. Queen to g2. No, yeah, queen to g2 works. Nice. Black to move. Easy. Okay, I think it looks like is anybody still here? Or is the stream just not loading for anybody? Can you just type in the chat if you're still here? Dang, nobody is here. Big rip. Okay, I think I'm going to stop the stream now then. Looks like everybody is left. Let's go to chatting. Any last thing? Is anybody still here? If anybody's still here, just let me know. Okay, it looks like everybody's gone. That's fine. Okay, good night. See everybody. I'm not sure when the next stream is going to be. I'll probably advertise it in the same places again. And yeah, look forward to seeing you all some other time. Bye.